Morning, everyone. So a year ago, I stood on the stage and talked about the benefits of explicit modularization and what we could build on top of that. But I may have glossed over some details that are a little bit of a wrinkle. So I'm going to recap some of the intro to last year's talk just to set the context, and then we'll dive into some of the details that I glossed over. So Clang and LLVM, well, Clang has had support for what we've generally referred to as header modules or module map modules for a while now. And it started off with Apple's implementation, mainly around optimizing things like Coco.h system headers. And then Google expanded that to support C++ and used a different kind of way of building modules. So I'm just going to sort of recap the reasons for modules and how we've used them. So we're all familiar with the C compilation model. You have a header file, you include it in some source files. The parser parses both those files independently and compiles them and does some redundant work in doing so, right? So figuring out all of foo's implementation and everything else happens in every compilation that includes that header file. This doesn't scale well. As you end up with more and more headers and more source files, you end up with a combinatorial kind of explosion in compile time and things like this. So the first attempt to address this in Clang and LLVM was a sort of a step above what had been done in some other compilers, where users, in this case, would describe the set of headers that could be compiled together independently. So there's a fairly backwards compatible. You accepted sort of limitations in the way you would write your C or C++ code, or Objective-C, etc. If you wrote headers in the way we all think of headers, nice and standalone and isolated, and they don't allow macros to infect their behavior and all of this, then you could turn this on. And the compiler would, build system tells the compiler to compile some source files. The compiler secretly notices that there is a module map and goes off and builds a reusable chunk of stuff, which is a binary file we call PCM, precompiled modules. And then the compilers can consume that and use it to do the rest of their work. This is cool. This is great. It's easy to ship. Build systems don't have to know anything about this. The compiler just does it all under the covers. Has some limitations. And the main one is parallelism. The build system doesn't see that this is happening, so the build system thought that it ran two different compiles. Both of those compiles stopped to go and run a single other compile. So you just used one core instead of two, and obviously this scales up and becomes more of a big deal the more parallel compiles you have. And because it's using, like, the compiler has been taught how to share these resources, and it's been taught how to do it using a local file system cache, it doesn't distribute at all. Like, there's no way to use this feature across multiple machines if you have a big compile farm like Google does. So when Google started using this, we moved to an explicit model where instead of the compiler conspiring with itself, the build system had to be taught about all of these things, which happened to be easy for us, not easy for like teaching the world of Xcode developers and all of their different tools how to do this sort of thing. And you had to pass the PCM files around between the compilations. So it looks more like this. Build system builds the reusable module, feeds that reusable module to compiles, and so on and so forth. But this is where I glossed over some details last year. So it sounds really cool when you're like, okay, yeah, it makes sense. The build system should know about these different tasks and it should pass things around. But what does that actually look like, actually having the build system know about all of this stuff that it's never had to know about before? Like, there's a diversity of build systems out there in the world. There's ninjas and makes and CMakes and different pieces of it. And they've all been pretty well used to dealing with a world in which header files go in user include. The build system doesn't even know that user include exists. The compiler knows where to go and look for header files, and that's how that has worked for decades. There's one extra wrinkle that makes this super difficult. Those PCM files, they are binary, they are version locked to the compiler and to the flags the compiler is using. So you cannot like distribute these when you distribute your library. You cannot like pre-compile them even for your platform, because if you pass different macros, if you have different build settings for like different size of integers. Those are different PCM files. So there's no way you can like go and put the PCM files next to the header files on your system. So even for the standard library, your build of your own personal foo project has to go and build a PCM for the standard library. And for, some random thing like zlib. Or for all of LLVM's like external interface if you happen to be writing some code that used LLVM. This is a huge increase in surface area for your build system to have to worry about. If it was just that you had to go and build PCM files for the libraries within your project, like if we're within LLVM, okay, not unreasonable, we might have to build LLVM asm parser.pcm, et cetera, et cetera. But now your build system has to run tasks for your dependencies that it never even had to know about previously. I perhaps should have said at the beginning of this talk doesn't have answers, it has questions. There are complications here without really good answers. Google has answers in the sense that Google's build system knows about everything. Like there is no concept of an external library inside Google's build system. In the Bazel open source version of that, there are external libraries, and there is no good answer to this today. So mostly this is about looking at the solutions that people have dabbled with and thinking about how they might be generalized or what the future might look like. One of them, if anyone has looked at how build systems work these days, GCC a long time ago figured out a way to interact with a standard make-based build system. The classic argument is called -mm or -md. There's a few variations on it. And that asks the compiler, when it is compiling a source file, to also spit out this little file, a .d file, that is like a fragment of make. That's kind of a special case, right? Your compiler is now very tied to its build system. But of course, this just evolved this way, and other build systems that know nothing about make files still use this system because it's a way to get that information out of the compiler. And what that fragment is just a little bit of dependency information. It just says, when I built this source file, I needed these header files. And that's really useful for the build system, because then the build system can notice, oh, this header file changed, I need to rebuild this. Usually this extra little fragment doesn't include anything about system headers. So if you reinstalled a system library, your build will be out of date and just running make won't do anything. You have to know, oh, I updated zlib, I need to actually like blow away my build, force a rebuild, so on and so forth. So we could build a version of -mm that works with modules, that gives the build system this huge fragment, maybe like multiple different targets that tell it how to build PCMs for all of the external libraries, all of the internal ones as well, potentially, or maybe not. If the build system already knows how to build internal dependencies, doesn't need to be told it by the compiler. But again, that's more surface area to what was previously a fairly simple little fragment of make that came out of that system. But it could provide exact dependency information. It'd be a little expensive. We'd have to do a pre-process up front. This system as it's used today, you don't go and run the compiler specifically just to ask for this information. You run the compiler to compile, and it, as a side effect, kicks out that information. So that's one option. Little bit of a performance problem in your build system. Maybe teaching it how to read more and complicated fragments of make might not be so much fun. The other one is what Google does. In an attempt to be as fast as possible, we have this thing called the include scanner. It is a sort of an approximate preprocessor. It doesn't know about all the hash defines and everything else, and so it'll come up with a rough overestimate of the modules that are required for a given compilation. And that's cool. It runs fast. It gives you a rough answer. You've got your build system that actually has the specific inter-library dependencies that can bound that kind of logic. But now you have less parallelism in your build because you've got these overestimates of what your build depends on. Not perfect either. Another one that's been kind of experimented with in the more in the C++ standardized modules, and I've not drawn a distinction so far between the kind of module map stuff, this backwards compatible module system that Clang and LLVM have had for a while, and what's being standardized in the C++ committee, which is a little different and has some nuances that I'll touch on in a moment. So this is an experiment that's been done in GCC by Nathan Sidwell. Kudos to him. And this starts to look a lot like the implicit modules system that we saw at the beginning, but it calls back into the build system. So it's lazy in the sense the compiler waits to figure out which modules it depends on, but instead of just orchestrating the building of those modules itself, it calls back into, over a local socket, some system that could be implemented by your build system, it could be implemented by your IDE, that has to satisfy the request for a module. So this is adding a lot of surface area between your compiler and your build system, but it is precise and it is fast in the sense that it tells you exactly which modules you need as soon as you know that you need them, and without running an extra process or an extra scan ahead of time. I don't know whether that's going to be the right answer long term, but it is one of a variety of things that are being thought about and experimented with in this space. So the difference between the modules TS syntax, or I don't know whether there's going to be a TS, I'm sure Richard Smith somewhere here will correct me if I've used the wrong terminology, and the module map world that we have today. The nice thing about the new C++ syntax for modules is that it's constrained, at least for new module imports. So when you go and write C++ code using this new C++ language feature that's not been standardized yet, the beginning of your file will list which modules you depend on and will not be able to use macros in certain ways. That means it's actually relatively cheap to go and discover, oh, which modules does this file depend on? I don't have to know how to parse all of C++. I don't even have to know how to do all the pre-processing or process the macros or anything else. I can look at that prefix in the head of the start of the file as a build system and go, oh, okay, these are the modules I need. But we've also moved away a little bit from some other problems, is that with the include model that we've had for decades, we've known where to go and look for header files. We've come to some agreements between build systems and package distribution and compilers. Header files go in places like user include. There is a search path. The compiler knows the search path, and it goes and looks for them. Modules aren't going to be like a text string in your C++ code that is like, here is the name of a file. It's going to be the logical name of an entity, much like using a namespace. And so now we're going to have to come up with some agreement between compilers and library vendors and build systems about what those names mean. Do they map to a dotted separated file path with a search path, much like the header include path? Is it the header include path? I think some people seem to have some misgivings about header include paths and how those searches cause performance issues for builds and compiles. So maybe this is an opportunity to get ourselves away from that, but it's not totally clear to me if and how we would. But yeah, so having those prefixes might make some of this simpler than the module map world that we have to live with at the moment. But it's not quite clear to me how that works. There's also a concept of legacy modules, which are like file names. And so you'd search for them, but then you'd probably have to use something like a module map to identify the groupings of header files that would go together to make it one of these legacy modules that look more like exactly what we've been living with in Clang and LLVM today. So that's actually a lot of information in a really short period of time. And I hope people have questions and thoughts and discussions. I know a few of the people who've been contributing to this, Nathan Sidwell and Richard Smith and other folks on the C++ Standards Committee are here. I will try to answer the questions as best I can, but also I might end up punting to the audience. The purpose of this talk was mostly just to describe the unknowns in this space that hopefully we will find solutions for. And maybe it's not as scary as I make it out to be. The whole -mm system kind of evolved and became quite a useful system for build systems to interact with the compiler, and GCC and Clang both now adopt that, and different build systems can now interact with that, ninjas and makes and all of that sort of thing. So maybe we'll end up with a solution that it ends up evolving more like that rather than trying to come up with some well-designed, formalized interaction between compilers and build systems. I'm just not sure. So thanks, everyone, for listening.
Okay, we have time for questions.
A few minutes here and there. Questions, thoughts, rants, fear-mongering? Indeed, indeed. Nathan?
Hi, I'll ask a question then.
Thank you.
So, one of the fundamental new things about module stuff, particularly with the legacy modules things, is that now, in the general case, it's not possible to upfront have the build system figure out, oh, I've got to go and do these jobs, I'll go away and do them. During that process now with modules, you discover new dependencies. And that, I think, is the fundamental newness of this module stuff, is that the dependency graph grows during compilation. And even with pre-scanning, you can't get that right. You could overestimate, probably.
Right. So, well, yes. Yes and no and yes. Okay. Certainly, as I mentioned, like the module mapper technique that you've implemented is, I think, the fastest and correct, right? Like it provides the exact answers you need as soon as you could know them without doing extra work. I know the Apple folks are playing around with trying to get out of the implicit modules build system into a more explicit modules build system, and will be hopefully upstreaming a tool that would, for the pre-TS header modules world that Clang and LLVM have been providing for a while, that would be precise, but it would be inefficient in the sense that you would have to do a pre-scan. Now, I mean, they're doing lots of stuff to make that really fast, but I just mean in a formal inefficiency sense. Pre-scan could be quite quick, and it can be correct in the sense that, hey, we already today could do all of the header includes. Like, we can go and pre-process the file and find all of the header includes correctly, precisely. And so we could do the same thing for legacy modules in the sense that we could do what looks like a pre-process of the file and get the right answer, I think. I could be wrong. Does that sound like it's sort of touching on what you're concerned with?
Yeah, I think so. It does seem sadly inefficient to have to go and do this pre-scan.
Yes.
And you're going to find this information again later.
Right.
Which is where this whole module map idea came from in the middle of compilation.
For sure.
I'm going to ask something, and then it's not my problem anymore. Which is why I like it.
Indeed. And -mm does the same thing, right? Like it defers to that compilation to then provide the information about which headers you depend on. Because the build system doesn't need to know which headers you depend on for the first compile. The object file isn't there, it just runs the compiler. And now it knows next time, oh, if this header file changes, yeah, you're going to need to rebuild. So certainly the module mapper idea goes along with -mm and things like that of find the information out when the compiler needs it. So I can certainly appreciate that. And if we can get build systems integrating with that, I think it'll be great. I think we're still going to need to come to some agreement about where module files go, how they're looked up, things like that, as much as that the module mapper removes those particular choices from the build system, from the compiler, and pushes into the build system. At some point, someone's going to need to come up with some answers around that.
Yeah, just so people know that the tooling group, SG15, is looking at this kind of stuff and addressing how do other tools, not just compilers, but code analysis tools, which may have slightly different requirements to a compiler.
Yes.
Answer the same set of questions. It would be good to have the same system being able to do all these needs.
Definitely.
Lots of different systems and a combinatorial explosion of build systems and compilation systems and analysis systems is not going to scale.
All the pieces, to be sure.
Thanks.
No, thank you.
Yeah, hi. I know this is probably a massive undertaking, but has there been any talks about standardizing on the binary format of the precompiled modules so that the systems will provide them as part of the...
I did gloss over that a little bit in the talk. I did try to emphasize it, but so some of this history comes out of obviously where LLVM came from in terms of basically building a serialized AST, lazily loaded, high efficiency I mean, storage-wise, they can take up more space than the header files, but because they have indexes in them and all of this, they can be quite efficient. But they're super version locked to the compiler version. Like as soon as we modify the AST, like this layout of classes that are used to represent the AST, breaks. And generally vendors, except for Microsoft a little bit, Microsoft has been shipping some binary module, essentially their equivalent of PCM files, for a few standard build configurations, like for debug and standard optimization. But I don't know how resilient those are. I don't know which flags you could turn on that would cause you not to be able to reuse those pre-shipped modes. But certainly with Clang and GCC, we've been reticent to entertain that idea because trying to come up with a common representation of the nuance and complexity of C++ across multiple compilers seems super hard and super restricting to those implementations. So at the moment, we're all...
I was just going to say, one of the problems is that pieces of C++ are implementation defined.
Yeah, you would have to come up with a very generic scheme that would allow extensibility a lot, and then they probably wouldn't be terribly reusable. Like, you'd have the reusable version that would have to like drop all sorts of details because you built it with GCC, but now you want to build with Clang, and so Clang can't see into certain bits of source code because GCC didn't care about those bits of code. It's a space we would seriously want to avoid if we can. But that does produce all these other complexities where building random project has to build a whole bunch of dependencies. Indeed. Like, what are you going to serialize? Marshall was just mentioning Microsoft's compiler, MSVC, CL.exe, didn't have an AST. It was a streaming kind of process, so far as I understand it. Yes, until recently. So now it does. But these compiler architectures vary a lot. Trying to come up with a common, efficient on-disk representation for them seems highly questionable. Any other questions or thoughts? You can always grab me after this and we can just banter as well. Otherwise, thanks for coming.
All right. Thanks again.